Hello, in this video we're going to talk about some of the theorems on convergence sequences. These are some important theorems on convergence sequences that will be used throughout the course when discussing sequences and also functions. Later on we're going to use these to talk about functions and continuous functions specifically. The first theorem is that the limit of every convergence sequence is unique. In other words, you cannot have a sequence an that converges to two different numbers. And that seems like it must be intuitively obvious, but of course we need to provide a proof for that. So let's see why that is the case. Let's assume that that is not the case. Let's assume that a sequence an converges to both a and b. So in other words, we know that the sequence must get very close to A, and it also must get very close to B. So that cannot be the case. So it cannot be the case that AN is both close to A and also close to B. So why is it that it's not the case? Because if AN is close to A, then if AN is close to B, then AN cannot be close to A. How do we articulate that? We could take epsilon to be in a way that if you go epsilon this way and epsilon this way, you're going to not reach A or B. So we want epsilon plus epsilon to be less than B minus A, or absolute value of B minus A. So we can take, or even equal would be fine. We can take our epsilon to be A minus B. Okay, so we can now turn that into a formal proof. So suppose that is not the case. So suppose on the contrary, so this would be a proof by contradiction. So on the contrary, suppose AN converges to A and also converges to B for some sequence AN and two real numbers A and B. If that were to be the case, we could use the definition of limit with epsilon equals A minus B over 2 and then get a contradiction as we discussed on the right. So let epsilon be absolute value of A minus B in the definition of limit. So what we get is there is some natural number n such that for every n greater than or equal to n, an minus a is less than epsilon, which is absolute value of a minus b. And there is some natural number m such that for every m greater than or equal to n, absolute value of a n minus b is less than a absolute value of a minus b. Okay, so I would have to specify that a and b are the same. So I would have to specify a is not the same as b, since I'm doing proof by contradiction. So now the place that I'm using the fact that a and b are not the same is the fact that epsilon is positive. And of course in the definition of limit I need epsilon to be positive. And after I do that, then I know I have these inequalities. So now I'm gonna prove that that is not the case. So take some integer, and this would have to be m. Take some integer more than both m and n. So take some k inside n such that k is greater than or equal to maximum of m and n using the Archimedean property. So this tells us that so by these two I will call that star, and I will call this one to a double star. By star we get, and of course I meant to say epsilon is b minus a minus b over 2. Okay, So by star I have AK minus A is less than A minus B over 2, and by double star I will have AK minus B is less than A minus B over 2. And what I'm going to get is, if I add these two, I would get absolute value of A minus B is greater than absolute value of AK minus A plus AK minus B. Now, if you rewrite the first one as A minus AK, you would be able to use the triangle inequality. So this is the triangle inequality. And when you add them up, AK's cancel. So we get A minus B. So this means A minus B is greater than, absolute value of A minus B is greater than itself, which is a contradiction. And of course this contradiction proves that the two limits cannot be different. The limit is unique. A and B cannot be different. Okay, so this is like the most basic theorem for limits of sequences. The next thing that we're going to talk about, the next property of convergent sequences that we're going to talk about, is that convergent sequences are bounded. So we say a sequence is bounded if it consists, if the set consisting of all of its terms is a bounded sequence, a bounded set. So in other words, the elements of the sequence are between two numbers, between A and B. Then we say the sequence is bounded. It turns out that every convergent sequence is bounded. So we are going to again talk about why that must be true, and then we're going to write down a rigorous proof for that. Okay, so since we know that sequence is convergent, all of the terms of the sequence must be around A, except for finitely many. So if you take some epsilon, let's say epsilon equals 1, all of the terms are going to be here, except for finitely many that are outside. But what do we do with those? All we need to do is to make sure that those are finitely many. We know they are finitely many, so there is some maximum and there is some minimum. So then it would be the terms of the sequence an would be between a plus 1, the larger of a plus 1 and the maximum of those remaining elements, and the smaller of a minus 1 and the minimum of those remaining elements. And we can articulate that this way. So suppose an converges to A where A is a real number. Let epsilon be 1 in the definition of limit. So what we know is that there is some natural number n such that for every n in n that is greater than or equal to n, an minus a is less than epsilon, which is in this case 1. So if you take an, there are a couple different ways of doing this one. One way would be to say an is between a plus 1 and a minus 1. This is for n starting from n plus 1, etc. So that tells us that for every integer m, an would be, if you take a1 all the way to a capital N minus 1 and a minus 1, am would be greater than or equal to this, because everything from a1 to an minus 1 is included here, and everything after is included in here. Everything after is more than a minus 1. And on the other side, it would be less than or equal to the maximum of a1 through an minus 1 and a plus 1. So the first terms are less than this, and the remaining terms are less than a plus 1. And this completes the proof. So what we showed so far was that if you have a sequence that is convergent, then the limit is unique, and every sequence that is convergent is bounded. The next thing we're going to do is to prove the comparison lemma. Some of you have seen this one in single variable calculus as the squeeze theorem. This is an equivalent of the squeeze theorem. Okay, so let's see what it says. We have two sequences an and bn, and what we know is the sequence an minus a is less than or equal to c times bn minus b in absolute value. A and b and c are constant. If bn approaches b, which means this approaches 0, then this side would also approach 0. In other words, an approaches a. By the idea of the squeeze theorem that you have seen, it makes sense. But now, how do we in fact prove this? Let's step back and see what we are trying to prove. So what we're trying to prove is we're trying to prove an approaches a, which means an minus a is less than epsilon. This is what we're trying to prove. In order to prove an minus a is small, we know that bn minus b is small. And then multiplying by c, we would be able to make that small. So what we need is c times bn minus b to be less than epsilon. And this gives us bn minus b is less than epsilon over c. There is a little bit of problem here. Think about why there's a problem here for a second. Of course, clearly one issue is that c could be 0. Okay, the other issue and more important issue is that c could be negative. If c is negative, then you have to flip the direction of inequality. So that's problematic. However, if c is negative, then c times absolute value of bn minus b is going to be less than or equal to 0. And that tells us that an is equal to a, which means limit of an is equal to a anyway. So we're going to have to take two cases, when c is positive and when c is non-positive. Okay, so let's just start with, again, we're trying to prove an approaches a. We're going to have to start with epsilon being positive. So we will take two cases. Case 1 is when c is negative or 0. Then an minus a, which is less than or equal to cbn minus b, is less than or equal to 0. C is less than or equal to 0. Bn minus b in absolute value is greater than or equal to 0. Which means an minus a is between 0 and negative 0. So that means an equals a for all n greater than or equal to n. The assumption was for all n greater than or equal to n, an minus a is less than or equal to c times absolute value of bn minus b. So that means an minus a is 0, which is less than epsilon for all n greater than or equal to n. And that tells us an approaches a. So this is the first case. This is the case when c is non-positive. If c is positive, then we have to employ the idea of dividing by c. So that's the second case. By definition of limit, there is some integer m such that bn minus b is less than epsilon over m for all epsilon over, c. If we go back here, we had epsilon over c. for all n greater than or equal to m. Now, by the Archimedean property, or we could just use the largest of the capital N and capital M. If n is greater than or equal to maximum of n and m, then absolute value of a n minus a is less than or equal to c absolute value of bn minus b, which is less than c epsilon over c, which is epsilon. So that means a n minus a in absolute value is less than epsilon. Therefore, a n approaches a. And that's exactly what we wanted to show. We wanted to show that if the larger sequence approaches, if the larger sequence bn approaches b, then the smaller one approaches a. Okay, this is going to be very handy. We're going to use that quite a bit. Okay, so one thing that the comparison lemma shows is that if you have two sequences that differ by only finitely many terms, then their limits are the same. So if you have a first few terms, you can ignore, because the assumption is for every n greater than or equal to n. So the limit really has something to do with the tail of the sequence rather than the first initial terms. So that's one thing. And finally, the last thing we're going to talk about is the relationship between subsequences and sequences. If you take a sequence an, then if you just take a few terms of that sequence, of course infinitely many, then that would be called a subsequence. However, you have to be always careful that when you're taking subsequences, they are in order. The indices must be in order. So the formal definition is let an be a sequence and n1 less than n2 less than n3 and so on be a sequence of positive integers. Then the sequence a sub nk given below, an1, an2, and an3 and so on, is called a subsequence of an. For example, if you take all of the positive integers, which is an equals n, then all of the odd integers 2n minus 1 is a subsequence of that sequence. All of the even integers, positive integers, would also be another subsequence. Okay. The last theorem is the relation between a subsequence and sequence. If an is a sequence that converges to a, then every subsequence of an also converges to a. So we know that an converges to a, and we want to show that a and k also converges to a. And the proof of this one is not very difficult. So suppose a and k is a subsequence of an. Let epsilon be positive. So what we want to show is that a and k minus a is less than epsilon, but we know a n minus a is less than epsilon, so that basically settles it. So by definition of limit, there is some natural number n such that if n is greater than or equal to n, then the distance between an and a is less than epsilon. So now, if n sub k is greater than or equal to n, then a and k minus a is less than epsilon, which is why a and k approaches a. So if we take k to be large, then a and k approaches a. So in other words, if k is large, let's say greater than or equal to n, then nk, which is at least the kth element, is also greater than or equal to n. So that tells us that if you have a subsequence, the limit of the subsequence, if the sequence converges, then the subsequence also converges, and it converges to the same limit. So that brings me to the end of this video. Okay, so if you would like to continue with this class, feel free to subscribe the channel, and I will see you in the next video.